Okay, class, this is a lecture on electric fields. We just learned about charges and how they have forces that either will attract charges or repel, depending on their positive or negative. And so now I want to talk about electric field. So basically, it's the field of this force. Okay, so a field is a way of conceptualizing and mapping a force that surrounds any object and acts on any other object at a distance without any physical connection. That's what I was trying to explain in a lab about the invisible field lines. So, for example, gravitational field surrounding the Earth and all masses represents the gravitational force that would be experienced if another mass were placed at a given point in another field. Basically, what they're saying is very similar to gravity. Gravity is a force, and it would have field lines that pulls us towards the center of the Earth. We just do not feel the force or see the force fields. So, just like the Coulomb's force equation here, we can solve for the electric field. So the electric field, there's two different equations. The electric field can either be referred to, the electric field would be the force, that's the Coulomb's law force we just calculated, over the test charge. So if you have a charge and you have the force, then you can calculate the electric field. A lot of times though, you're not going to have the force. So what you can do is it's a substitution. You substitute the actual Coulomb's law equation in for F in the electric field equation, and you can see just here from below that you basically delete the little q and you're basically left with the electric field is the K times a big charge divided by the distance they are apart squared. So the electric field depends on the charge we'll call capital Q and the distance r, and the little charge, test charge, gets deleted out. So I just wanted to go over two problems that they have in the book before I give you a worksheet. And the worksheet should be fairly simple. So we want to calculate the strength and direction of the electric field, so that's the E, due to a point charge that's 2 nanocoulombs at a distance of 5 millimeters from the charge. So what I suggest you do is start underlining your numbers and then try and identify your knowns. So this is a charge because it's coulomb, so that's a Q. And then this is the distance, so that's an R. So you can find the electric field by using this equation, E equals K Q over R squared. Why? Because the other equation has the force in it and we were not given any force. So then if you plug in everything to this equation, you're going to get 7.19 times 10 to the 5 newtons per coulomb. That's very strong. It's almost a mega. So I just wanted to let you know. And also the unit for the electric field will be newtons coulombs. Another calculation here, example, is doing the other equation. So what force does the electric field found in the previous example exert on a point charge that's 0.25 microcoulombs, and that's negative. So they're going to use the E value from the other equation, from the other problem. So now you have a little q and you have an E. So all you have to do is rearrange this equation and you're left with F equals QE. Notice the negative is there because the charge was negative to begin with. And that becomes 0.18 newtons. Because the Q is negative, the force is directed in the opposite direction of the field. So a force is attractive as expected, like charges. The field was created by a positive charge and therefore acts on a negative charge. The changes in this example are typical of common static electricity, and most forces obtained are similar to forces experienced like static cling and other things. So you can go forward. I really love this. You should try doing this. I have fun. I like doing this FET as well. And that's really a cool topic. So I am going to be assigning a homework for this as well.